Our project is on adaptive welding robot for multi-material semiconductor packages. Our team is Jacqueline, Anish, Sankar,
Anish
Destiny.
Shankar.
Yeah.
Destiny Aguilar.
Huaiyu Ma.
This is from the Semiconductor Skill Bridge Academy at Ohlone College. Our faculty coaches and mentors are Rose Margaret and industry mentors from arm engineers is Chris Lamb and Vignesh. This is our team slide. My name is Jacqueline. I'm a major in aerospace engineering.
My name is Anish Shankar. I'm a major in finance and statistics.
My name is Huaiyu. I'm a math major.
I'm Destiny. I'm a mechanical engineering major.
For the agenda slide, we'll be going over the introduction, literature review, system and architecture and technical frameworks, robot simulation, and conclusion. First, we'll be talking through the introduction for our adaptive welding robots. So, one of the 3 points is adaptive welding robots are automated through the welding process using integrating coding. The robot has an implementation of laser scanners, vision systems, and thermal monitoring. There's monitors that process the welding in real time, and this is adjusted through multiple parameters that allow for complex welds without the sacrifice of precision. It also differs from traditional automated welding due to its dynamic of nature.
So why does the topic matter? So first of all, semiconductors are the backbone of modern technologies. From EVs to AI servers, they are heavily relied on semiconductor packaging. And second, uh, there is a need for a flexible and smart manufacturing, which is what we call a Industry 4.0. And lastly, this is important also for a sustainability and resource efficiency. So a better adaptive control could lead to less material and energy waste, which could help to reach our goal with sustainability. So some of the problems are first, compatibility. Different thermal conductivities and expansion coefficient could lead to microcracks or wrapping during welding. Second, adaptive control and process optimization. Very complicated ML and AI algorithm for dynamic adjustments for laser power. And this is especially in a condition where less data are available. And second, assert precision and microscale challenges. Semiconductor packaging require really extreme position where robot position and path planning must be ultra accurate. And fourth, integration with semiconductor manufacturing environment. So welding generates spatters, which could lead to water contamination, where a clean room compatibility design are required.
This is a literature review. Existing studies and frameworks. So existing studies include trial and error of utilizing these new smart technologies in manufacturing, lots of learning errors from AI, But once a mistake is made in real time, AI will learn from the mistakes, and then robots were able to improve upon any errors and prevent repetition of mistake. Next is the material recognition. So material recognition is the process of a robotic arm using sensors and other tools to accurately pick out the material it is working with. It tells other components to speed up, lower, or turn up the heat. Having a robot that can adapt to these different materials in semiconductor manufacturing could result in a better product and decrease future failures due to material unalignment. So now we have the,
So we have the system and architecture. Oh, I'm so sorry.
oh, that's okay. We have the system architecture and technical framework, which we all worked on. So.
Oh, so for our system and architecture and technical framework, as you can see, this is a diagram of our schematic of adaptive welding robot. And as you can see, the diagram shows a lot of where like the robot will move in from like the Y to the X and Z. Basically this shows well, the drawing doesn't show it, but we'll be talking about how Beta has a closed loop for control process, which allows the adjustments of welding with the parameters in real time. And basically this mimics the movement of how real time a person can experience in welding.
Next is the Cortex-A microcontroller. So the Cortex-A microcontroller, it acts as the brains of the robot. It uses TensorFlow Lite to take into account weld quality and classify materials, powers machine vision systems, runs internal AI models, and synchronizes Cortex-M actions and data to flow better. Moving on to the ARM's Cortex-M microcontroller. So this microcontroller, it acts as the reflexes for a robotic arm. It does not take much power to run, and in return, it is very energy efficient. It's connected directly to motors, sensors, and communication buses, and with no other system to interfere in between. It can also control different aspects in just microseconds and in real time.
Our robot needs ROS because adaptive welding changes every millisecond. ROS is the backbone that links cameras, thermal sensors, AI on Cortex-A, and real-time control on Cortex-M. With ROS, the loop closes fast, system adapts to material and heat changes, and this helps with the weld quality and makes it stay consistent.
TensorFlow Lite for material recognition. So TensorFlow is a Python library and framework, and TensorFlow Lite can be effectively used for material recognition, especially in scenario where requiring on-device inferences like on-source constrained devices like mobile phones or embedded systems. And some benefits for using TensorFlow Lite for material recognitions are optimized performances and on-device capability and reduce resource consumption. And Cortex-A for AI inference. So Cortex-A CPU are widely used for AI inference, especially in mobile and embedded devices, by leveraging software layers like ARM neural network and the compute library for optimized neural network execution on these power-efficient processors. And while it's powerful, they also offer blend of performance for efficiency suitable for various models, from LLMs to smaller domain-specific AI. For specialized tasks, Cortex-A core can also be prepared with ARM's ethos NPUs and for even greater acceleration and efficiency. So thanks to Chris that introduced us with what basic of AI is. This is on the left, this is what a neural network is, which is given input and output, and we're trying to find a function that maps the input to the output.
So other slides defined what Cortex-A and Cortex-M were. This slide shows how they work together. So ROS is the bridge. Cortex-A runs AI and publishes commands, while Cortex-M executes real-time motor and welding control. Sensors feedback through ROS each cycle. The loop keeps the system more adaptive. So system architecture summary. So ROS is essential for adaptive welding that changes every millisecond. It is a communication backbone linking cameras, thermal sensors on Cortex-A, and real-time control on Cortex-M. AI infers weld parameters and sends commands as well. Cortex-M executes precise motor and welding adjustments. ROS closes the feedback loop so the robot adapts to different materials and thermal conditions in time. The result is consistent, welds less scrap, and a scalable data-driven system for modern semiconductor manufacturing.
This is the robot simulation video. All right, so in this video, it's just a simple program. It's similar to what we might see in the industry. Right now, it's just using the welding tool to make a box, but this is similar to what it might be like for the robot to weld for semiconductors. And so that's just a little bit that we learned during our classes, and we utilized the Robo Guide, which is the digital twin to our welding robot, in order to simulate what it might feel like in the real world. So here's our conclusion. What we learned. Thanks to ARM microchip incorporation, welding robots are efficiently able to use sensors to construct semiconductors and semiconducting materials. Models like the Cortex-M and Cortex-A work together in the robot to act like the brain and body. AI and robots allow them to calculate and prevent failures in real time. With smart manufacturing, welding robots will keep improving, and the process of manufacturing semiconductors will only improve along with technological advancements. And here are our references, which I'll just go over for a few seconds.
Those are acknowledgements.
And we just wanted to say thank you to all our mentors who helped us out, all the ARM engineers, all of our professors. It was very enlightening and we learned a lot. And I'll open up the floor for any of my other colleagues to talk about their appreciation.
Yeah, so I just wanted to thank the program for supplying us with all this information, as well as Professor Itua for guiding us through this new information. And you can all, if you have any questions, you can always contact us on LinkedIn. We have all our names on the intro slide, so you can find us on LinkedIn, and feel free to give us a message if you have any questions. Thank you.
I would also want to thank the ARM engineers that helped us throughout our process and actually, and
I want to thank the program for introducing us to the ARM engineers. They taught us a lot of real professional knowledges that could potentially help us in our career.